Hello, everyone. Welcome to New York Combinatorics seminar. We are very happy to have with us today Simon Vilmin from France. He is my collaborator of recent years, so I'm very happy that he's giving a talk today for us. We started working since about 3 years ago. And since then, Simon became a permanent member of computer science department at University of Marseille. And so today he will present some results from our first joint paper. So please welcome.
So yeah, thank you very much. And hello, everyone. Thank you for having me today. So yeah, I'm going to talk about finite closure systems and special kind of representation, which is called a D-base. And as a preliminary introduction, I would like to say that maybe closure systems are not well known yet. You might be interested for the reason that closure systems are mostly everywhere, namely that when you deal with, say, matroids or convexity, logic, algebra, argumentation, database, FCA, all kind of stuff, lattices, of course, then somehow you are dealing with closure systems, which might be of interest then because closure systems allow you to talk many languages at the same time, and closure systems and of course their representations. So the talk will be divided in two parts. So first question, what is the D-base and what are closure systems, which is like the topic of the title of the talk. And second part, I will try to outline at least one of the idea we developed. But I think the first part will take some time just to give you the intuitions of how do we work with closure systems. So first question, what is the D-base? And to answer this question, we need to know what is a closure system. So a closure system, so I'm dealing only with finite objects. So you have a ground set, which is called X, say, and a closure system is just a set system over X, which contains X, the ground set, and which is closed under intersections. So when you represent the family F using inclusion, like the Haas diagram, the PO set, you obtain what we call a closure lattice, or just a lattice, say. And the members of F are usually called closed sets, closed set. So you have a picture on the left, you have a closure lattice. The ground set is A, B, C, D, F. For instance, BDF is a closed set. It is the closure of BDF because the closure system induces a closure operator, which associates to each set the inclusion-wise minimal closed set that contains it. And you see, for instance, on the diagram that if you take the intersection of, say, ABD and BE, you obtain B, which is also closed, which is closure under intersection. A detail that will be important later, it's whenever F is also closed under union, if it's closed both under intersection and union, then it is called distributive closure system, which will be important later. So this is a closure system, and an easy way to read, say, closure systems from their diagrams is say that we withdraw labels and we replace, we just label the closure of each element by their elements. So for instance, I label A, the closure of A, C, the closure of C, and so on. Now, in order to read the closure operator, like to read closed sets and so on, you just select a point or a subset of the ground set, say BC in this case, and you try to locate the minimal point above both B and C, and this will be the closed set. And here you see that BC is the union of all the labels that are below, so everything which is below phi of BC is A, B, C, D, F. So this is a convenient way to read closure systems and diagrams and so on, but it's also on purpose that I describe this. It's because if we stick to BC, we see that phi of BC, the closure of BC, captures, say, AD and F, which we can write as implications. BD implies A, BC implies D, BC implies F. So I will formally state what is an implication later, but so far it's just a way to express that a subset of X will capture some elements outside when we'll take its closure. And so now, because implication somehow translates the closure operator, it's some kind of way of expliciting, like making explicit the closure operator. A natural idea is to try to describe the structure of the closure system or the lattice equivalently by means of these implications. So I'll do a bit of history now because it's not like a recent question, nor it is an ad hoc question. And I will take the history starting from lattice side, even though many fields have different history. But in fact, this question finds its root in already like in the previous work of Dilworth in the 40s, when he was working on trying to describe some lattices based on special, what we call irreducible element decompositions, which I will not detail, but that was the origin of the question. That was a bit later studied studied by Finkbeiner, where he defines in his papers, he defines in terms of lattices what we'll call implications. And then it turns out this question of describing lattices by implications has at least two branches, one on the side of what we call semi-distributive lattices with, say, Johnson and Nation in 77, or from the perspective of semi-modular lattices with, say, Gaskill and Rival in 78. And this kept on moving on, like we have Day in 79, Feigl on the semi-modular side of 86, JB Nation, who is here in the audience, who describe which might be what is the closest in terms of lattices of what we'll describe later, the D-base. And all of these works, except maybe the semi-modular ones, are somehow summarized in the book on free lattices that came up in 95. So this was for the lattice part. And then in 2013, this went into the field of more combinatorial, like computer science, say, by moving to set systems and closure systems and implications and so on. So this was a work of Kira and JB also, where they translated the ideas from lattices to implications and closure systems. And since then, some algorithmic works has been conducted, like trying to compute the D-base from implications or from data. And what we did here is try to investigate through the lens of output-sensitive complexity, the problems like algorithmic problems of computing the D-base, may it be from implications or irreducible closed set that I will define later. And before moving to further definition, maybe a glimpse of what happens in other fields. So I said at the beginning that closure systems are everywhere. And in fact, this question of describing closure systems by implications is also everywhere. So for instance, if you're acquainted with logic, then this question is the same as finding a Horn CNF for a pure Horn function, is the same as finding functional dependencies, association rules, and so on. And it also generalizes, say, finding the circuits of a matroid or the minimal transversals or vertex covers of a graph or a hypergraph, for instance. So this question is really everywhere. So back to implications, like it's time to formalize a bit what I was saying before. So an implication over my ground set X is a statement A implies X, where A is a subset of X and X an element. And an implicational base, an IB, usually, is a pair X sigma, where sigma is just a set of implications over X. So it turns out, if I take any IB, X sigma, it defines a closure system whose closed sets are exactly the sets that satisfy all the implications, where satisfy mean if I have the premise, the left-hand side of an implication, then I also have its conclusion. So any IB defines a closure system. And on the other hand, any closure system, any lattice, can be represented by several equivalent implicational bases. There is a lot of possible choices of implicational bases to describe the same closure system. And the idea on this side is the one that I was depicting you before. It's to say that an implication is true. A implies X, when X is captured by the closure of A. So on our example, this could look like this. So on the left-hand side, we have our example, A, B, C, D, and so on. And on the right-hand side, we have a possible implicational base for my closure system. So we have C implies A, and B implies D, D implies B, and so on and so forth. So to go from the lattice to the implicational base, I use what we saw before. So X is in the closure of A, and to build the lattice out of the implicational base, we use forward chaining, which is somehow transitive closure. Say, so you start from some set and you add conclusions as long as you have unsatisfied implications. And this will help you build the whole closure system. So I told you that a same closure system can be represented by a huge amount of implicational bases, different ones. And here is a small amount of all the possible implicational bases that can represent a closure system. And it turns out, so I won't go in too much details, but in the big picture here, you can separate them in two sides. You have those that satisfy some properties that mostly come from logic. So you have an implicational base and you want to optimize its size, its left-hand size, its right-hand size, and so on, its Horn minimization. And you also have a bunch of what I call structural implicational bases that aim to capture some special aspect of the lattice and which turns out to produce a good implicational basis. So namely the canonical, which has been studied in the 80s, which is minimum, E-base, D-base, generic, and so on. So there is a lot of different implicational bases. But us, we are here. Today, we want to focus on this one, which is called the D-base, and that comes from lattices. So I will first try to give the intuition of what is the D-base, and then I will give the formal explanations. So the intuition behind the D-base is, okay, we want to describe a closure system by means of implications. Now, a natural idea for this is to take each element of the ground set and try to find all possible minimal explanations for this element. And by minimal explanations, I somehow mean the minimal ways of deriving this element. So to define this, I will need two ingredients. First, I will need to describe how elements of X are ordered in the lattice. So you see in the picture on the right, which is our running example, you have A, which is below C, which means that A is in the closure of C, and you have, say, D is below F. So you have others. But this order between the element of X will be translated into binary implications. So an implication is binary when it consists of a singleton on the left and a singleton on the right. So you have small implications. And this already encodes somehow singletons explanations, like an element gives another one. So this is the first ingredient. We encode the order that represent the elements of X in the closure system. The second type of explanations is what happens when a subset of elements captures my elements, say here F, but without being above. So for instance, C, D, E, none of them are above F. So F is below no one, no CDE, yet CDE captures F. So this is some kind of another explanation. But it turns out, if I look more carefully, CD, which is a subset of CDE, is also an explanation for F, which means that CDE is not minimal. But then if I look closer at the order of the lattice, it turns out I can refine CD, that is, I can go down in the lattice and change D for B, which means, yes, D for B, which means that BC refines CD, and that CD in this sense is not minimal, because I can find someone else below that will still produce F. And these minimal explanations, this is what I call minimal explanations, are precisely what we will call D generators. And these will be the implications that will go into the D base. So to sum up like the intuition, the D base that I will define right after is just composed of two elements. So first the order on X, C implies A, F implies D, and so on. And then all these minimal explanations of each element that are called D generators. So now it's time to make it a bit more formal. So we first need to define what's called the binary part of a closure system. It's simply put, it's the closure system which is represented by the valid binary implications. So you have a closure system, you have an order on X, which gives you small binary implications, and the binary part of the closure system is the closure system which is represented by these binary implications. So on the left, we still have our lattice with the 5 binary implications, C implies A, F implies D, and so on. And on the right, you have what happens when you take the closure system represented only by these implications. And this is what I call the binary part of my closure system. Interestingly, and it must be actually, my initial closure system must be included in its binary part. Any closed set of the initial lattice is closed for the binary part. Second, I need to formalize D generators, and then I can define the D base. So what I call a D generator is I try to formalize this idea of minimal explanation. So I take a set A, and I say that it is a D generator if A is not above X, a D generator of X, sorry, if it's not above X, that is, it does not follow from these simple implications, the order on X, and if it is minimal for this property. So it is in phi of A, it is not below A, and it is minimal for this property, meaning that, to summarize, say, if I take any other set, which would be below A, any other set B, which is below A, with the meaning I was giving before, then X does not follow from B. So this is what is written in the two statements here. It allows to encode what I called minimality. So D generator is simply those minimal explanations for each X. And so now the D base is just the composition of the two ingredients I talked about earlier. So you take binary implications to encode the order, and then you take all these possible explanations, all these D generators for each element. And this is the D base. And so why does it work? Like, we take a huge amount of implications, and why do they necessarily like represent faithfully the closure system? So an IB represent a closure system where when it does correctly describe the closure operator. So we just need to argue that if I take each Y and I try to compute its closure with sigma, like the implication, then I will obtain the right closed set. So for this, you take any Y, and a simple observation is that every element which is captured by Y follows from some minimal explanation at some point. Any element which is captured by Y has an explanation in Y. So now from the D base, you have your binary implications that allow you to go down in the lattice by following them. And because we put every possible explanations in the D base, then it must be that any possible explanation for any X captured by Y is in the D base. This explains that the D base is correct. So on our example, the D base would look like that. So we have, again, our binary implications. And on the right, we have each line corresponds to the D generator of someone. So we have DE, which is the only D generator of A. And for D, we have AB and so on. And we recognize the BC example that I was giving at the beginning, which is indeed a D generator. That is, it cannot be minimized again. So this is the D base of a closure system. This is how it's represented. Based on this, I can now move to how do we compute the D base from what we call irreducible closed sets. So now I take a new example, simpler one, actually, where we have less binary implications, so we have only two. So recall that I do some kind of simplifications to read the closure system. So I have the real closure system on the left, the simplified reading on the right. And I have two then binary implication, D implies C and E implies C. And its D base, trust me, the D generators, trust me, are on the right. These are the correct ones. So an irreducible closed set is a closed set that I cannot obtain by taking intersections. So remember that a closure system is a set system which is closed under taking intersections and that contains the ground set. And an irreducible closed set is exactly those closed sets that I cannot obtain by intersection, meaning that if I take a closure system and I remove an irreducible closed set, then I will lose some information. So we have the illustration on our two examples below. You see they are the blue guys. And you can easily recognize them from the diagram because they are exactly those closed sets with a unique parent above. And irreducible closed sets are interesting because they form the unique minimal subset of my closure system from which I can rebuild my whole closure system using intersection. So doing it slowly, I already said that yeah, okay, so say I have a closure system and I want to find a concise representation based on closed sets. So I will start to remove closed sets that I will consider useless, meaning that if I remove a closed set, I still have enough information to find it back by taking intersections. I cannot remove irreducible closed sets because I said that they are not obtained by intersection. So if I remove them, I will lose some information. And it turns out that any other closed set can be obtained using intersection of irreducible elements. This makes irreducible closed sets very important because they are the unique subset of closed sets that I can use to rebuild my whole closure system. From a more applied perspective, say you have binary data. So here I have on the left customers in a shop, like anyone, and you have products in columns. And across means that the customer bought some product. So here in yellow, you see that Lille bought product C. So this is usually what we call transactions in data mining. And it turns out these binary data encode a closure system. So you see, if I say that each row is a closed set of some closure system, and I take all possible intersections, so then I will obtain a closure system, of course. And it turns out, in particular, I only have irreducible here, but okay. And now what's interesting is that a rule, what we usually call a rule in the data, is in fact precisely a valid implication of my closure system. So for instance, the implication AB implies C of the closure system precisely mean that in my database, my transactions, whenever a person buys both A and B, then he or she also buys C. And this gives another motivation for studying computing the D-base from irreducible closed set. It's because it has some implications from the data mining point of view. So the two problems that we have been studying with Kira and Louari Nourin are the following one. You are given a set of irreducible elements of a closure system, and you want to find the D-base. You are given an implicational base, any one. Remember that you can have a huge amount of equivalent implicational bases for a same closure system. So you are given an IB, and you want to find the D-base. And this is usually what we call enumeration tasks. We do not seek to decide something or to optimize something. We want to find a set of solutions. We want to list all the solutions, all the implications of the D-base, without repetitions, of course. So further motivations, if any. So another good point of the D-base is that it falls into the scope of what I call structural IBs, and so it unveils some hindsight, some ideas on how the lattice is built. So it conveys structural information on my structure, and it has the good taste of being ordered direct, meaning that we can compute closure very fast, basically. And it turns out it has already some practical uses. So some sea breeze forecasts, so for city nearby yours, and also for some medical stomach cancer estimations. So it's still well motivated. So now we'll have some kind of a small problem for my two like enumeration tasks. It's that in general, the amount of solutions I want to find, like the D base, what I want to find is exponential, as size exponential in terms of what I have as input. So let's say you are given an implicational base, any one, and you want to compute the D base. The D base can be of size exponential in what you have. So take this example. You have a ground set which is A1 to AN, B1 to BN, C1 to CN, and D. And you build these small implications which are pictured in the center. You have A1, B1 implies C1, A2, B2 implies C2, and so on and so forth. And you also have C1 to Cn implies D. So you have a small amount of implications. O of n, something like that. Yet, if you want to compute the D base, then you will have to produce an exponential amount of implications, because here, the D base consists in sigma plus any choice of Ci or Ai, Bi for each I. It's like the binary words on Ai, Bi, Ci. Because each of these binary words in red gives a D generator of D. So this means that any algorithm that will start from an implicational base and build a D base must have exponential time complexity. And as a consequence, input sensitive complexity, that is giving the complexity of my algorithm only in terms of the size of the input, is not very relevant because it does not help to understand how hard is the problem. And this is why we have output sensitive complexity. So an enumeration task, a bit more formally, is you have some input, x, and you want to list a set of solutions. Here, each solution is of polynomial size with respect to x, and you want to list a set of solutions R of x. So let's say we have an enumeration algorithm, which has input of size n and m solutions. We will look at the execution time of A. And I will say that my algorithm, A, has output polynomial time if it runs in polynomial time in the size of the input and the output. So you see the yellow guys here, the small dash, are exactly when a solution is printed. So when an algorithm is output polynomial, it means like, okay, I have an algorithm that runs in the size, polynomial time, the size of the input and the output. But this definition is not completely satisfying because sometimes you want to have a new solution at a regular, regular amount of time. So we'd like to have a delay between two solutions, which is some kind of regular and not too far, not too big actually. And when we have a delay between two solutions that is bounded by a polynomial in the size of the input, then we say that our algorithm has polynomial delay, which is some kind of the gold standard we can aim for when we talk about enumeration. It's got some kind of the best we can hope for. And this is better because the output polynomial case, maybe you will have a huge amount of time during which we'll have no solutions, and at the end, all the solution will be produced. When you have polynomial delay, you know that at each polynomial amount of time, you will have a new solution, which is much better. And finally, I will need another kind of complexity, which is output quasi-polynomial. So it's the same as output polynomial, instead that you replace polynomial by quasi-polynomial. So these are the notions of complexity that I'm going to use. So now, going back to my two problems, what has been done for the problem of finding the D base from irreducible elements? It turns out Kira and JB gave an algorithm in 2017 which uses hypergraph dualization. It turns out this algorithm may produce a possibly large, in fact exponential, amount of implications that will need to be discarded. So it's not an exact algorithm. It gives a superset of what I want, and sometimes too large. For the other problem, if I have a set of implications and I want to find the d-base, which is another set of implications, there has been an algorithm in 2015 and a bit more refined in 17, which uses simplification logic, but it's only studied from an input-sensitive point of view, and it also produces solution to discard. On the other hand, when we have a look at what has been done in database community, it turns out there is a related algorithm that finds, say, the d-generator of some element, using a technique which is called in enumeration as solution graph traversal. So now what are our results? For the first problem, you have irreducible element and you want to find the d-base. Then we show that we can have a output quasi-polynomial time. To do this, we use dualization of distributive lattices and a recent algorithm by El-Bassioni that solves this problem in output quasi-polynomial time. For the second problem, we obtain polynomial delay, and we use this algorithm coming from database that I was talking about a bit earlier. So I will focus on the first problem, and if I have time and if you want to, then I could take some time to talk about the second approach. So I want to focus now on the problem of you have irreducible element and you want to find the d-base. And to do this, I'll need to talk about a problem which is called dualization. So on the left, you have a lattice. And in this lattice, I'm going to take two anti-chains that I will call B plus and B minus. So an anti-chain is a set of closed sets which are pairwise incomparable by inclusion. So I have my two anti-chains, B minus and B plus. And I say that these two anti-chains are dual if every other closed set is either above B minus, which is the purple part, like the up arrow B minus, or below B plus. So in another way to say this is to say that my two anti-chains partition the lattice into two parts, an upper one and a lower one. And these anti-chains are called dual. And now the problem of dualization is you are given a set of implications, an implicational base and an anti-chain of the corresponding lattice, B plus, you are given B plus, and you want to find B minus. This is dualization. So you are given the green one, the blue one, B plus, and sigma, and you want to find B minus. So what's the complexity of this problem? If you take Boolean lattices, that is power sets, then in fact, this problem is very well known. It's called hypergraph dualization, and it's likely one of the, arguably the most important problem of algorithmic enumeration so far. It's open for like 40 to 40 years, I think, something like that. And the best algorithm we have today is quasi-polynomial. We do not know whether the problem is hard or not. It's still open to decide it. And the best algorithm we have is quasi-polynomial. So we think it's unlikely to be hard, but we do not know. This is hypergraph dualization, or also known as monotone dualization in logic. A bit more general is dualization of distributive lattices. Remember that distributive means closed under intersection and union. And this, a recent result by El-Bassioni shows that it also admits a quasi-polynomial time algorithm. It's not the same as the one of Friedman and Cachin for hypergraph dualization. It's another one. And when you go to more general type of lattices, then it's known to be hard. Like there is no output polynomial time algorithm unless P equals NP, which is the hardness of enumeration. And it turns out we are right here for our D-base enumeration. The two problems are equivalent. And this is what I'm going to picture right now. I'll try to picture it right now. So first, how do we show that the problem of finding D-base from irreducible element reduces to dualized distributive lattices? In fact, remember the binary part of the closure system. It's the closure system represented only by the binary implications. It turns out this closure system is distributive, always. So here on the left, you have the binary part of my new example of the second part, which has only two implications, D implies C and E implies C. Now, if I look at the degenerators of some element, say A, they will define an anti-chain in this distributive lattice. And this correspondence is bijective. I mean, each degenerator will produce a unique element in the anti-chain. And I also add A, because we can consider that it is a trivial degenerator for itself. So this defines a B minus. And interestingly, the dual anti-chain, the B plus, is a subset of irreducible closed sets, which are part of my input. And they are precisely those irreducible elements that are inclusion-wise maximal to avoid A. So here, if you look on the right-hand side below, you have A, and if you take BC, CD, and CE, they are irreducible, they do not contain A, and they are maximal for this property. Any closed set above will always contain A. In convex geometries, this is usually what we call a copoint attached to a point. Still, you see that my degenerators and A and the maximal irreducible closed set that do not contain A form dual anti-chain in a distributive lattice. And this shows how to reduce the problem of finding the D base to dualization of distributive lattices. So this is the one side. To show the other side, you start from a distributive lattice, say the implicational base of a distributive lattice, but that consists only, it will always consist of binary implications, so that's okay. And you are given the famous B plus. You are given the blue anti-chain. And we want to find the purple one. So we want to reduce this to finding the degenerators of some element in some other lattice, not too complicated. A remark, I told you that I need to reduce to a problem which has irreducible as input and not implications. But it turns out for distributive lattice is okay. I mean, given implications or irreducible is kind of the same. So I can safely say that I have irreducible elements here. And so the trick to reduce my problem of dualization to finding the D base of someone is to do what we call doubling. So we'll double everything which is below someone of B plus, like the flower below B plus. We'll find some kind of doubling operation by adding some gadget Z to the universe and pretend that B plus is precisely these maximal irreducible element without Z that I was talking before. And so not going into too many details now, it turns out my closure operator precisely defined a bijection between B minus and my degenerators of Z. Meaning that starting from a distributive lattice, we perform some doubling, like correct doubling, and it turns out we obtain that the degenerators of the resulting closure system exactly defines the anti-chain B minus that I want to find. And this shows that dualization of distributive lattices reduces to finding the D base of some closure systems, not too complicated. So I think, yeah. Yeah. And so to conclude on this problem, we have that given irreducible elements, we can find the D base of the associated closure system in quasi-polynomial time, output quasi-polynomial time, using well-known algorithms to dualize distributive lattices. So now, yeah, I will conclude. So the D base is a way to describe a lattice by, so I did not give the name, but what we call in lattice theory minimal joint covers, but this means minimal explanations. It is a natural way of describing a lattice, a closure operator, by putting all possible explanations in a set of, in form of implications. It turns out it has really good properties, computational ones, all the while giving some insight on how the lattice is structured. So what's about finding the d-base from different representation of a closure system? So we studied two. We have output quasi-polynomial time if we are given irreducible elements, so those closed sets that cannot obtain by intersection. And we have polynomial delay if I'm given another set of implications. So I did not detail this one because it's a bit longer. So what's left now, and what we have been working on a bit still, it's a subset of the d-base, which was called the e-base, that also comes from lattices, and that, unlike the d-base, is not always correct. And so a natural question is then to characterize lattices and closure system with a valid e-base, and maybe try to find algorithms, much as what we did with the d-base for the e-base. And yeah, I think that's all. Thank you very much for your attention.
Thank you, Simon. Do we have any questions?